All right, let's take an example, or not an example, but a definition that you may have seen in college algebra and definitely would have seen in pre-calculus. Is a definition of a strictly increasing function. We say f is strictly increasing on an interval I for each x1 and x2 in I. If x1 is less than x2, then their outputs are also less than, then f of x1 is less than f of x2, so that inequality is preserved over the function. So if we have an interval I, x1 and x2, you can see that f of x1 is less than f of x2, and that's just the picture for increasing functions. So if I pick an x1 and x2, x1 smaller, then the output of f of x1, that output is going to be smaller than the output of f of x2. Okay, decreasing is just the opposite. If x1 is less than x2, then because it's going down, since it's going down from x1 to x2, f of x1 is going to be larger than f of x2. And then for constant, they would just be equal. So let's look at a result here. Let f be continuous on a closed interval AB and differentiable on the open interval AB. F prime of x is greater than 0 on AB implies that f is increasing on the closed interval AB. So notice that it has the assumptions that the mean value theorem required. Mean value required that f was continuous on the closed interval AB and differentiable on the open interval AB. So the mean value theorem is going to be pretty important in this proof too. In order to prove something's increasing on an interval, we have to pick two random points. We'll do an x1 and x2, and the x1 will be smaller than x2, and we'll have to use the mean value theorem to somehow show that f of x1 is less than f of x2. So that's what we're going to try to do here. So we're going to let x1 and x2 be in the open interval AB, and suppose that x1 is less than x2. Okay, since x1 and x2 are in the closed interval, or in the open interval AB, the closed interval x1, x2 is going to fit in there, so we can use the mean value theorem. And so there's going to exist a C in the open interval x1, x2 such that the tangent line at C is going to be equal to the secant line connecting x1 and x2. And since we're making the assumption that the derivative is positive in AB, because C is in x1, x2, which is in AB, f prime of C is going to be positive. So that means f of x2 minus f of x1 all over x2 minus x1 is also positive. Now x2 minus x1 is already positive, so the only way we can have a fraction being positive is both negative and negative in the numerator and the denominator, or positive and positive in the numerator and the denominator. Since x2 minus x1 is positive, that forces f of x2 minus f of x1 to be positive also. So f of x2 is going to be greater than f of x1. In order for that to be positive, f of x2 has to be larger. And this fits our definition of a strictly increasing. x1 is less than x2 implies that f of x2 is greater than f of x1. So we do have, in fact, that this is increasing. Now, the arguments for decreasing and constant are real similar. So let's just suppose that we have pretty much the same setup, other than our derivative will be negative. We'll say, in this case, f is increasing on AB. So if we go to the next page here, we'll look at the other cases. If f of x2 minus f of x1 all over x2 minus x1 is less than 0, then again we're going to have the same setup. X2 minus x2 is greater than x1, so same setup as the first one. Now x2 minus x1 is positive, and the fraction there, this fraction is negative. So the only way this can be negative is if the numerator is negative. So that means that f of x2 minus f of x1 has to be negative. So then that means f of x2 is less than f of x1, and that's going to imply that f is decreasing on the closed interval AB. Okay. Now for constant, our derivative would be equal to 0. So we have our f prime of c is equal to this secant line, or secant slope, and that's going to be equal to 0. The only time a fraction is equal to 0 is if the numerator is equal to 0. So that would tell us that f of x2 minus f of x1 is equal to 0. And so that would be giving us that f of x2 equals f of x1. And that gives us, that is constant on that interval. Okay, we're going to look at the first derivative test, and this is real helpful in locating extrema. So normally what we're going to end up doing is we're going to be finding all the critical numbers of a function, and that's where the function's not differentiable. That doesn't mean that we're not looking for where the function was not defined, but it was defined but not differentiable, and then where the derivative was equal to 0. And then what we're going to look for is around that critical number, what does the derivative look like? Is it positive or negative? And that's going to tell us some things about whether we have extrema or not. So we need a couple things. Let f be continuous on an open interval I, and let c be a critical number of f on I. If f is differentiable on an interval containing c except possibly at c, so we're going to assume that this interval is within our interval I, then f of c is, and it's going to be one of the following. It's going to be a max if f prime of x changes from positive to negative. So remember, if the derivative was positive, that meant we were increasing, and then if it's negative, it means we're decreasing. So we went from increasing to decreasing, so we'd have a max. It's a min if it goes from, if f prime of x changes from negative, which would be decreasing, to positive, which would be increasing, so we'd have a minimum. Or it's not a min or a max if f prime of x does not change signs. So that could be a possibility also. Okay, so we'll do the proof for just the maximum one. The one for minimum is real similar, and then not min or max. We don't have enough to really show it either way. We can do some examples or something where it wouldn't be a min or a max. Anyways, let the closed interval AB be an interval that containing c, for which f is differentiable on the open interval AB, except possibly at c, because we might have like a corner or cusp. So we saw some examples of like the absolute value function has a corner at 0, but that is also a minimum. If f prime of x is less than 0 on the closed interval AC, maybe we could say it's the open interval, but anyways, I won't get into too many details, but we'll just say it's differentiable. We should say it's differentiable on the open, so let's change that, because we don't know if it's differentiable at C, so we're going to make a minor change here, so make this open interval AC. Then, from the last result or theorem that we had, we knew that f is decreasing on AC, and f of c would be less than or equal to, but since we were talking about strictly, we'll just say f of c is less than f of x for all x in AC. If f prime of x is greater than 0 on CB, so c is just somewhere in the interval, and then again we should make this open here. Then f is increasing on CB, and f of c is less than or equal to. It's not wrong to say less than or equal to, but we were dealing with strict inequality, so we'll go ahead and just make it a strict inequality for all x and I. Thus, f of c is less than or equal to f of x for all x in AB. So we can say less than or equal to because c is now in that closed interval. So f of c comma c is a minimum. I think I said maximum on accident earlier, but we're doing the minimum case. So if we're going from decreasing, to increasing, that's not a very good picture. Decreasing to increasing, we're going to have a minimum somewhere. So that's the picture associated with this.